Hello, my name is Dr. Michael Kelly, and this presentation is about the use of portfolio diversification by using graph theory within Mathematica so that we can build a portfolio based upon a number of assets and bonds, but diversify them so as to minimize the risk. The idea here is to get a graphical representation of the correlation between the various assets that make up a portfolio. But in addition to that, to use the vertices that can and their axes that connect the vertices to represent the strength of the correlation between the various assets. So we'll be concerned with the concept of diversification. We'll set up a very simple sample portfolio to emphasize this point. Then we'll move on to the concept of graphs and networks with a short introduction, which I will look at the Mathematica help file in order to introduce these ideas of graphs. Then the application of concepts from graphs to portfolio diversification within finance, and then its deployment, showing the ideas of how correlation will change over time as the values of the assets change. And also the concept here of building up a portfolio that's built upon the notion of correlation thresholding. That is to say, what assets we include in the portfolio will be determined by the degree to which they're correlated or not correlated. And there'll be a certain cutoff threshold within the correlation levels. So the idea here is to reduce the investment risk with diversification. If you think about the nature of setting up an investment portfolio, you don't want to have yourself exposed to the possibility that a number of assets, because they're highly correlated in a positive manner, if just one of them starts to go down, then all of them will go down, and your returns will be minimized. So you want to have a degree of independence between them. This is the concept of setting up a rather large portfolio and the use of indices within the financial industry. So what we're going to do is look at different ways we can explore this diversification by using visual correlates. So the idea here is to set up a very simple portfolio. It's going to consist of 3 elements. Okay, these consist of the S&P 500, the SPDR Gold Trust, and PIMCO Exchange Traded Fund Trust. So it's a very simple case. We're only going to look at 3 entities making up our portfolio. The idea behind this is to introduce you to a particular case so you can get used to the concepts. Then we'll generalize it to many of the entities that belong to the Dow Index. So here we're using the function financial data. Just a quick explanation of what financial data is. So with Mathematica, you can quickly find out about financial data. The financial data function accesses an enormous range of financial instruments and gives you a range of properties dealing with them. What we're going to be interested in is the closing prices and the returns. But financial data also accesses a lot of other information in addition to this. And this can be seen by looking at the help file. So you can see that in addition to these other simple values, we also return important information such as volatilities, cumulative returns, fractional changes over different periods, as well as fundamental related properties like the price to earnings ratio and the PEG ratio and market capitalization and so on. So going back to our notebook now, what we're going to do then is we're setting up a function. This is a pure function. Mathematica is able to set up pure constructs. It will map onto each of the elements in our portfolio, and it'll ask for the financial returns for the period from the beginning of 2010 up to the current date. And usually it returns an ordered pair, in which the first element is the timestamp and the second element is the actual value. Here we're only interested in the values, because we're only interested in looking at the returns. So what we're now going to do is, having got these returns, I'm going to map another pure function onto each of these returns. We're going to be looking at the histogram function so we can see what is the nature of the return for each of these elements. In particular, I'm going to be looking at their probability density function. So in other words, their probability distribution. I will stack them all together in a graphics row. And so we can see here for our three components that are the basis of our portfolio, you can see that they have a similar type of normal distributions. What we're interested in is the nature of the correlation between these various assets. So that's what we're going to do here. We'll take all of the returns, but at the moment, what we've got is lists. So this is going to, the actual return is going to be a 3 sublists. I then transpose this so I get a list of pairs, and I look at a list of triples, sorry, and I then look at the correlation between each of these elements. So I can then look at this result within the table format. And this is the result that we get. So this is the recent values for gold and the exchange traded funds and the spider values. And we see here that, of course, that each of them has perfect correlation with itself, as would be expected. Okay, whereas the others either have some negative correlation, and the other aspect to notice about this, of course, is that it's a symmetric matrix. The correlation matrix is going, so the correlation that exists between the GSBC and TUZ must be the same as exists between TUZ and the GSBC. And we see here that the correlations are of the order of about 10 to 26%. Okay, another way to think about this is to go back and, in the same way as beforehand, looking at the correlations between each of these triples to set up a matrix plot. Okay, and so we see here that this is where we had perfect correlation. And here, the different colors indicate different degrees of correlation. So the blue here indicates the same and a higher level of correlation that existed between the other elements. Okay, so what we want to do is take this simple portfolio, of course, and extend it to a much more generalized example. One that consists of all the elements in the Dow index. So to give you an idea of then what a matrix plot for a much more complex portfolio would look like, let's consider the matrix plot associated with 100 by 100 entities. In this case, the entities are random real numbers taken from the real line between -1 and +1. So we're just basically getting any type of correlations. Correlations, of course, will take values between -1 and +1. And in evaluating this, we see that this is the type of structure that we see. So you can get a whole range, and we're going to be using this type of notion in order to identify the structure of negative and positive correlations and cutoff thresholds that will determine which assets we'll include in our portfolio. So we're going to be using concepts from graphs and networks. At this point, it's interesting just to step aside and look at what Mathematica has to say about graphs and networks. If we go back into the help file, this can be easily accessed by going to the beginning and looking at Mathematica's collection of mathematical algorithms, and going down here and looking up graphs and networks. And what we see is that there's an enormous amount of functionality that Mathematica has in this area. In particular, we're going to be looking at the construction of simple graphs. The other thing that's going to be important here is looking at the correlation between individual assets. In mathematical terms, these are called adjacency graphs. So we're going to be looking at this as well. And the other point that we're interested in is there's going to be certain subsets of assets that are correlated positively or negatively. And we want to find out what these connected subsets are. Okay, so this also comes into a special group called components and connectivity, and we're looking at the connected components. So just a quick description of what Mathematica has to say in these areas. So all of these, as with all of the capabilities in Mathematica, are expressed as functions. You've got a graph in which you specify all of the edges in the graph, or two subsets. One is the collection of vertices and the corresponding collection of edges that connect these vertices. So here, for instance, I've got an undirected graph consisting of 3 vertices, and this is the list of their edges. So 1 is connected to 2, 2 is connected to 3, and 3 is connected to 1. A directed graph is the same, except instead of having a bilateral type of relationship here, the connection only goes in one way. We can see this a bit better if I recalculate it, make it a lot larger, and we can see that there are arrows here that there weren't in the previous relationship. So in this case, the elements, the vertices, are actually going to be assets in the financial example that we're interested in. And we're going to be looking at undirected graphs, because if asset 1 is correlated to asset 2, then asset 2 is correlated to asset 1 with the same strength. And so the edge, which is a measure of the connection between them, which is also going to be a measure of the weights that we'll use in our portfolio, is going to be the same. The other notion that we're going to be using is going and looking at the matrices. So we've already looked at matrices that measure the correlations between the various assets. And this measures the extent to which one component or one vertex or asset is connected to another one. So this is called the adjacency graph. What you do is you specify the adjacency matrix, which in our case is going to be the collection of correlations between all of the assets. And what's understood here is that the vertices are actually going to be the assets that go into our portfolio. So here, for instance, here's a matrix. For those of you who are unfamiliar with Mathematica, it writes everything as a collection of lists. So a matrix is actually a list of sublists. So we can take this particular matrix, and I can look at it in matrix form. So this is the typical form for such a matrix that's usually represented in most maths textbooks. And what we're saying here is that there are 3 vertices. The first vertex is connected to the third one. The second vertex is connected to the first one. And the third vertex is connected to the second one. And we have this relationship here. So I want to use this idea, and the last notion that we'll be using in connection with portfolio diversification is the concept that there are going to be, when we analyze all of the assets in our portfolio, there are going to be some that are positively correlated in a similar fashion, others that are negatively correlated in a similar fashion, and yet others that are completely disconnected with all of the others. So in order to understand this, I've got to be able to look at what are called the connected components. So Mathematica goes into this in quite a lot of detail and has a lot of functionality associated with that. What we're interested in is just specifying the connected components in any graph. So here, for instance, we've got a complete graph, which by definition means that all of the elements, all of the vertices are connected. So when I ask for the connected components in this 5-element complete graph, I get it is the list of all of the connected elements. With this one, however, you can see it's a directed graph, and the connected components are slightly different. So here we can see that 1, 2, and 3 are all connected to one another, but 4 and 5 are separate. So we're going to be using this notion, and lastly, we want to be able to represent our connected graphs within the overall graph. So we want to be able to highlight the connected graphs. and those particular assets within all of the collection of all of the assets that we're going to be putting into our portfolio. So there's a simple way to do this. You specify the original graph, and then you specify a subset of vertices within that graph that you want to highlight. So here, for instance, only vertices 1, 2, and 3 are highlighted. There's a number of different ways this can be done. You can also highlight the edges, as we can see here. So we'll be using this notion as well. So now going back into our notebook, we'll look at this example here. So we go back to our simple example of a matrix in which we have, so this is telling us, this is our adjacency matrix, and it's telling us that the first vertex, or the first asset, is linked or correlated to the second one, that the second asset is correlated with the third one, and that the third asset is correlated with the first one. Okay, then what I'm going to be able to do is represent this adjacency matrix in its normal table form, and we'll put each of the corresponding vertices on the top and on the left hand side. Okay, and we get this type of relationship here. So this is easier to understand. If we see that vertex 1 is connected to vertex 2, vertex 2 to vertex 3, and vertex 3 to vertex 1. And in fact, we can now show that. This is our adjacency matrix. We put it inside our adjacency graph. We're going to label each of the vertices with their names, and this is what it looks like. Just make it a bit larger. And in this manner, we'll now replace the vertices with actual assets to look at the nature of their relationship. So what we want to do then is to take this concept of an adjacency matrix, but transfer it over to the corresponding ideas dealing with assets and their correlation. So we want to have an adjacency matrix associated with a portfolio. So I'm going to define a thing called a portfolio matrix that depends upon a certain level, a cutoff value for the correlation. So I go back to my financial data, I get all of the returns, and I look at their correlations, and this is given by my portfolio correlation that we've already established previously. Then I go into this, and what I want to remove is all the elements that lie along the main diagonal. We already know that each asset is perfectly correlated with itself, so I put a 0 in that place. Then I'm going to look at every other element that's inside our adjacency matrix. In Mathematica, we use the notation x underscore or x blank. Now, Mathematica can do this because it is a pattern matching program. And this is really shorthand notation for any object to which we give the name x. So what we're saying is that if theta is our correlation, we will assume that for all elements that have at least a correlation of level theta, that they be replaced by 1, which will signify that they're connected. Otherwise, if their correlation is less than theta, they are not connected, and will give in the adjacency matrix a value of 0 for this. So this is taking our portfolio correlation for the returns in each of their assets and turning the correlation between those assets into values within an adjacency matrix. So we have our original portfolio correlation. I'm going to show you now what the portfolio matrix for this would be when we assume that the cutoff value is 0. In other words, if there is any correlation at all, then we'll assume that those assets are connected in some way. And this is what it looks like. So you can see here, these have already been replaced by zeros. And all of these, because we're looking at whether or not there is a positive correlation. So the negative values go to 0, and all of the positive values goes to 1s. So we see we've now got an adjacency matrix that is also giving us information on the nature of the correlation. Not only the nature of the correlation between the assets, but a sort of cutoff level. So we're saying we'll include only those values that have a positive correlation and ignore those that have a negative correlation. Okay, we can emphasize this then by showing a one-to-one correspondence between the adjacency matrix and each of the corresponding elements. So our portfolio consists of only these 3 elements here, and the way in which they'd be represented as a graph. So we see that, as is the case here, each one is connected to the other one, and this simple graph tells us that information. So we'll now look at applying the various ideas that we've had to the particular case of portfolio diversification. So we're going to generalize what we've had previously and include now all of the members in the Dow index. We're going to include additional commodities such as gold and silver and coffee and the rest, and a number of bonds, bonds from Australia, Canada, Germany, and treasuries. And I will join all of these together to create one large portfolio. What I'm interested in, of course, is not just the portfolio, but the returns. So I use the financial data function, and I map it onto each of the elements in the big portfolio. So instead of the hash argument here, it will take each of the elements we see here and find its return. Its return values going from the beginning of 2012 up to the current date. And I'm interested just in the values of these returns. Now what I get as a result is a list of sublists, where each sublist is the returns for each of the assets. If I transpose this, I'm going to convert this into a list of n tuples, where each n tuple lists the corresponding returns on the same date for each of these assets. I can then take the correlation of this to find what is the correlation between each of the assets. And in this way, I get a correlation matrix. Then we're going to undertake the same type of transformation that we had previously, but generalize it now to this large correlation matrix for the big portfolio. So I'm going to set up a big portfolio matrix, which is the adjacency matrix for the construction of the portfolio. It says, let's go into each of the elements, and the matrix basically can be represented by elements in which we indicate the ijth element being the element in the ith row and the jth column. And it says, let's look at all the elements along the main diagonal and replace them by 0. So in this sense, we're saying I'm not interested in having edges which are circular going from one vertex to another to itself, because that's a given. And look at all other elements, all other correlation values, and compare them with a fixed correlation value theta, which becomes our threshold correlation value. If any element in our correlation matrix is greater than theta, then replace it by 1. So this now becomes an adjacency value telling us that there is a connection or an edge between one asset and another. For any other value that lies is less than theta, then replace it by 0, telling us that there is no connection or edge between those two assets. So in this way, we take a correlation matrix and convert it into an adjacency matrix. The adjacency matrix depends upon a certain cutoff value for theta. For those values less than this cutoff value, then they will be represented as being unconnected within the graph. And for those values that are greater than the cutoff value theta, they will be represented as being connected within the graph. So now we can see how this works out. What I'm going to do now is look at our adjacency matrix for our large portfolio and have a cutoff value of 0.5, a correlation value of 0.5. So we're saying then that for all of those assets whose correlation is less than 0.5, then so far as we're concerned, they're not connected. And they'll be represented as individual elements. For all values greater, they will be connected, and there will be an edge between them. I'm going to use a particular graphical style here that is predefined, so in order to emphasize the nature of this connection. And this is what we get. So we see here that there are free connected subgroups. Sorry, 4 connected subgroups. This is the largest. This is the second largest. And we have these 2 simple groups here. And everything else is disconnected, which means that all of these elements had a less than 0.5 or 50% correlation with any of the other elements in the graph. So what we're looking at is that these elements are all strongly correlated with one another here. These are all strongly correlated with one another. So are these 2, and all the others are not highly correlated. So I want to use this information now. We can go into more details and extract the connected components in the following way. What we do is we say, let's go into each graph G, and I want to look at the corresponding subgraph using the same graphical style. The subgraph will be chosen from a table or list. So here's our subgraph, and we're saying, well, let's find all of the connected components in the graph. And in particular, let's find all of those that match the following instances. Those instances where a connected graph is such that the length, the number of elements in it, is greater than 1. So I'm not interested in anything which is just the trivial case. I want to look at all of the non-trivial connected subgraphs. So I'm going to sort them in this way from the smallest to the largest. But really, if you think about it, it's really the largest ones, the ones that are most connected, that I'm interested in. So I want to reverse this sorting order. So now we are constructing a table consisting of all of the subgraphs, going from the largest connected subgraphs to the smallest connected subgraphs. So we can now look at each of these. This is the first and second subgraph, and this is saying let's look at the third to the last subgraphs. So here is the largest subgraph, and we can see that all of these elements now, this is the largest collection of assets in our portfolio that have at least a 0.5 correlation between each of the elements. This is the second largest subset. And here we have everything more or less left over. These are the elements, these are the only other remaining elements other than the trivial class, which we've excluded. Okay, so we said any connected graph that was just consisting of a single element really wasn't of any interest. So these are basically all of the elements, all of the assets in our portfolio that are highly correlated in the sense that their correlation is greater than the cutoff value, which was 0.5. All right, so what I really want to do, of course, is find in our graph all of those elements that are not in the connected graphs, that is the independent vertex set. And I want to highlight this. I'll do it in the following way. For each independent vertex set, I will represent it by a star. And then these stars will show up in the representation of the graph. So first, let's find all of those elements which were uncorrelated. So we've taken all of the original elements and numbered them to correspond to the vertices. This is all of those that were the independent or standalone elements. Now I'm going to show where, and we can see here how they show up when I represent the entire graph. Okay, so these are independent elements, and they're interesting for the construction of a portfolio, because what we want to do, of course, is buy more of these. If we buy things that are highly correlated and stack them together, then if the market shifts in one way, all of these will shift in the same way. So this would be good if all of their returns went up. But if, however, all of their returns go down, then we will make a massive loss. So the idea is really to diversify your portfolio by having more of these elements which are unconnected with each other. Okay, now I want to generalize this, and this really now applies to an instance where we've collected an enormous amount of data. So basically we've done the same. We've taken all of the elements of the Dow index plus a large number of commodities and bonds, and constructed very large portfolios. But we've done this at a succession of dates. Okay, so you can see that it is the same as before. We have a cutoff correlation, but I also have an additional argument n. And just as beforehand, here is going to be our correlation matrix, but it's not one matrix actually, it is now a collection of matrices. So this is stored data, which I'm uncompressing. This would correspond to an instance where you have a very large database, and you could use our function database link, which would then import this data, or you have some other source, such as the use of the Bloomberg link within the Wolfram Finance platform. So this would be a collection of returns at various times. And what we're interested in here is how does this collection change as we move through time? In other words, how does our portfolio change as we move through time? If it doesn't change much, then you can basically take a sit and hold position in your investment. However, if it does change, then you have to update and alter your portfolio, which corresponds to changing the weights of the portfolio or dumping certain elements and including others instead. And what we'll show is that this is indeed the case. Even if you fix theta, your cutoff value and your correlation, as we move through time and look at the same assets but at different points in time, then the correlation structure will change. So we now take all of this, and I'm going to again build an adjacency graph. So we're going to take the entire set of elements and then really look at the connected subcomponents. There's going to be two, when I'm going to be using Mathematica's manipulate function, and there's going to be two parameters in this, the n and the theta. Okay, don't pay too much attention to the rest of this. This is all basically window dressing. It all has to do with the manipulate function, which is just, let's quickly have a look at it. As you can see, this is one of Mathematica's super functions, and it really allows us to represent inside Mathematica any type of GUI function where you can specify the parameter that you're interested in, and allows you to dynamically adjust this parameter, and as a result, the function will be updated accordingly. Going back to our notebook, this is exactly what we're going to do here. We're going to look at the same time changing the cutoff correlation and the points in time at which we look at the behavior of the returns as we go from the past up to the present. So here we're going to be looking at the migration or change in correlation starting at the beginning of 2012. Okay, and basically this is going to be since January, February, March, and so on. So we're moving forward in time. And then the other parameter we're going to be looking at is the correlation threshold. Okay, I've included some additional options here. Sometimes when you have such very large sets, importing an enormous amount of data into the function can lead to some halting behavior in the graph or in the manipulate function. And that's why it's best to have asynchronous behavior. So we can now look at how this is behaving. Okay, so let's look again at all of the data, all of the returns between all of the assets since the beginning of 2012, and see how the correlation substructures change. Okay, and you can see that they change a hell of a lot. So if I make it a very small cutoff threshold, the smaller I make it, the more connected it's going to be. The idea is choosing that sweet spot. What is the value of theta? So that I'm going to get more and more disconnected components. Okay, as you can see here, it starts happening, basically, let's bring it down here, it starts happening really around 0.3. Then I'm starting to get more and more disconnected sets. And these are the ones that are of interest because being disconnected, having smaller correlations, they're less inclined to move in conjunction with other values. So these, for instance, are all going to move in the same direction simultaneously, as will these, and this together. But these others will remain indifferent to the movements. And so these are the ones we should be giving higher weights. What should be the value of the weights? Usually a good starting approach before you use optimization would be, say, the reciprocal of the correlation. Now note how this changes as we move through time. So again, let's go back to about a value of 0.35, and then let's move forward through time. Okay, so now as I'm moving forward through time, what do we observe? In this particular case, with this value of about 0.35, we always seem to have two quite large connected subsets. And so now it seems to be joining back together again as we're getting closer and closer. Okay, so apparently it starts off, they're all reasonably connected, then they start to drift apart and then join back together again. So this shows even more strongly that we should be choosing higher values for our correlation cutoff. If we go back again, we can see here this maintains. Okay, so again, it came to March 2012, things started to, the market obviously had a large amount of momentum, and correlation between elements, there was a higher number of highly correlated elements. So studying such graphs gives you a visual way of thinking about the elements in your portfolio. Which ones are moving in concert together, which ones are remaining independent. And again, this is then inversely related to the investment that should be placed in each. You don't want to overinvest in those elements that are going to be moving in the same direction. Works fine if all of them are going to be appreciating in value, but of course, if the market goes down, they'll all be decreasing in value and your portfolio will crash. So in this way, you can work out what is the structure of the relationship, not only in terms of correlation on their returns, but also the behavior as we move through time. So the notebook can be downloaded, and at the end, you'll see that there's also some further details that are basically just for the presentation of the material and the inclusion of the extra data set. So that concludes this talk, and I hope that you can learn from this how to use concepts from graph theory, and with the concept of an adjacency graph associated with portfolio investment, build up a diversified portfolio. Thank you very much.